And we should start the session now. All right, so let's start the session. So, do you have any questions for me before we start the session? No questions? Let me turn it off. Great, great. So, all right. So, yesterday we were talking about the word count problem and we were trying to figure out what could be the possible solutions. All right. Did you think of some more solutions than these two, three? One, we talked about programmatical way. Where what we were doing is we are reading the data from left to right and top to bottom, and then word by word, and we were checking in a in-memory maintained registry whether a particular word exists in the registry or not. If not, we add it into the registry, otherwise we increase its count. And once we are done with scanning the whole text, when we are done with when we are finished or we have reached the lowest point, we say that then we just print the registry to the end user. The second attempt was to basically use SQL to do the word count, right? Break down, prepare a table which has only a single column with the column is the word, and then we group by. All right. So first of all, let me be very clear why we are talking about a problem like sorting. Okay, these are basically sorting problems. All right, this is very important point. So maximum problem of the computing are related to sorting. Maximum problems which we encounter are related to sorting. Whether I'll start writing so that it becomes more interactive. All right. So a little background on what exactly are we doing. All right. It must be fourth session, right? This. Yeah. All right. Now, so what we talked about just before was related to a question related to sorting, and sorting being a very important problem. Okay, sorting being a very important problem. And why is it important? Because if you think about databases, okay, so when in a database, when we say where x equals to 10, okay, in our query, what does it mean? Okay, what does it mean? When we say select star from this table where x equals to 10, can sorting play a role in that? Anyone? When we write a query in SQL, and when we a query with simple filter saying select star from this table where x equals to 10, does it make use of sorting in any way? All right. Now let me ask a question. If there is an index on that column, will it be faster or slower? Faster, right? Now, what exactly is index? Index is nothing but data which has been sorted. All right? Index is nothing but a sorted data, whereby you could quickly scan through the data immediately. All right? So sorting does play a role when it comes to indexing. Yes, very good answers from all of you. Yes, that's correct. Mahesh, pointers to the location of specific data elements is something that index contain, but the data is ordered by certain order, and therefore, so do you, was I able to convince you that sorting impacts the where clause? All right. So every time you insert an item, every time you insert an item into a table, it impacts the index. Sometimes it might lead to resorting. Yes. All right. Now, second is that is our first point. Now, second is what about a command like order by? Is it impacted by sorting? If the sorting algorithm suddenly become faster, will order by be impacted? Yes, that's right. That's right. Yes, and Beshwa, that it is essentially sorting. Third is joins. Okay, when we join two tables, when you join two tables, there are many ways of joining two tables, right? One is you pick up a record from left hand side, you go over the right hand side and keep doing it again and again. All right? If say you have, okay, let's say you have two tables, one on the left hand side, other on the right hand side, and you have some record here. These are records. I'm just trying to do something and okay. So like these are the two records and I'm planning to join these. Okay, joining means for each record on this side we have to find out all the records on the right hand side which has the same column value, right? So one way would be that you pick up a record and go over the list, you go over each of this list and then link them. Okay, then say that okay, these two records are joined together. Then we go over second record and and again iterate again, and then we say okay, this and this are having same ID. And then same way we pick up the next record and go over the list one by one and then make a relation, okay, that these two records, this and this, these two records are same. Say they will be joined together. So what exactly am I trying to do? I'm trying to show you how the usual join works. But if you look at this situation here, it is com- far more complex. Okay, in the sense that it will take lot of time. It is of the order of if there are n record this side, m record this side, total number of comparison are going to be n into m. Okay, which is not great. But if you order one of these data sets, the bigger data set, if you sort it, then it'll be really fast. If you order this data, then you pick up a record, do a binary search on the right hand side, and quickly find the record. Then we pick up second record, do a binary search on the right hand side, and it'll be really, really fast. So the if you have to join it again and again, and the second table is ordered already, so the overall complexity will be n of log m. Okay, total number of comparison will be these many. So sorting, just because we have ordered, if you order this data, if you order the second data, ordering will take some time, but it will make your joins really fast. It will make your joins really fast. All right, so ordering, if you take the second data set and you make it ordered. Okay, if you take this, it'll how much time will it take to make it ordered? M into log of m. That's what it will take. Plus search joining will take these many this many time. So you can see that uh, my question to you is, if you have m into log m plus n into log m, which one is greater? Which one is greater? N into m or n log m plus m log m? Anyone? So which one is greater? N into m equals, which one is greater than? Okay, n log m plus m log m. Out of this side and this side, which one is greater? Or you can say here n plus m. Yes, that's correct. Yes, Anabe. N into m is bigger. Meaning, if you, okay, let me, for those who are not from computing background, yes, that's right, Mahesh. So n into m is bigger because log values are far more smaller. All right, log values are far more smaller. Except for n equals to 2 and m equals to 2, or n either of them being 1. Okay, that's the only situation where they are equal. Otherwise, in almost all scenarios, n into m will be bigger than n log m into m log m. Okay, for those who are not from the computing background, let me try to oversimplify it. So whenever we are doing any algorithm, we basically compute the total number of comparison that will go into doing something. And we generally consider two things. One is worst case scenario, other is average case scenario. And in most cases, we generally consider worst case scenario. So when you do a sorting algorithm such as merge sort or any of these standard, though there are many research that have gone into sorting, and every month, every year, every year there is some improvement or the other in the sorting algorithm. Okay, in the sorting algorithm, there is one improvement or the other every year. So sorting, though the problem has existed even before, even before the computers were invented, even before we knew of computers, we have been actually inventing new techniques of ordering data. All right, there is, I mean, when people used to play cards, there was a way of quickly ordering the cards, and then there were many, many more use cases of sorting in the real life even before computing. And most of the algorithms have been inspired by the real way of sorting. Okay, so there are many algorithms of the many strategies of ordering data. All right, one of them being you divide the data set into two halves. Okay, sort them individually, and then order them one after another. Okay, swap them if they are not ordered. If they are ordered, then okay, or merge them together. All right, there are many strategies I can describe to you in a different class. Yeah, so sorting being very important problem. There are two main algorithms. One is merge sort and quick sort. These are the two algorithms that are generally used for sorting. Okay, and the number of comparison it takes to sort n number of records is about n log n into logarithm of n. This logarithm is base to the power 2. All right, all right. And the time it takes to search a list, if you have a list of n records, if you have a list of n records, and if you have to find out one value in this n records, and this if this list of records is not ordered, it will take around n number of hops. You will first go from top to bottom, and whenever you find out a value, you will return. In the worst case scenario, it will take around n number of comparison, comparison to find a value in a list which is not ordered, right? But if the list is ordered, if you the list make the list ordered, then you have to you remember how we used to search a word in a dictionary in a normal life. So we pick up a word, we jump backward, we jump forward, and we keep on doing it quickly. Okay, so that's binary search. All right, so you if a list of if the list of things is sorted already, ordered already, then it's very easy to search something. You basically search in the beginning, then you search in the end, and then you search in the middle and check whether the current value is lesser or greater. If it is greater than the value you are expecting, that means you have to search in the first half, then you keep on doing it again and again. So every time your search space is becoming half, right? So in the middle, when you compare the value with the middle value, you will realize that okay, where this value is lesser than the value we are looking for. So now we have to search in the second half. If the value is bigger than the value you are looking for, that means you have to search in the first half. So that's how the searching in n number of records takes around log n. All right, takes around log n. And if you have a million record, searching in a million record will take around I mean, what was that? Okay, so if you have a million record, okay, this a million, and then if you do an ln of this, ln uh, ln of this, okay, so it comes out to be around these many comparisons. Okay, all right. So basically, in around 14 to 15 14 to 15 comparison, we will be able to find an element in a million records if the million records are ordered. So that is the power of binary search combined with sorting algorithm. Okay. So again, when we talk about joins, so joins is like picking a value from the one table, searching in the index of the another, right? If you have that kind of scenario, joins will immediately improve. All right. So joins are impacted in a big way, in the same way as the point number one is impacted by sorting. Okay. Now fourth is group by. Okay. Fourth is group by. Now if you think about group by, one way of doing the group by is you pick up a value, scan through the list, whosoever is having the same value, you group them together, and then you pick up the second value. Go through the list, find out whosoever is having the same value, then group them together. And you keep on doing again and again. Now, this exactly the way our join without sorting was slow. This approach will also be slow. This approach of picking up one value, going through the list, making the buckets, and saving them will be will be really slow. Okay, will be really slow, and therefore it can and therefore it cannot be used in case of production, because if you think of group by, it'll go through a list of elements uh, again and again, right? The same can be improved by sorting the data. If you sort the data, the same values, or the values which have the same ID or same some parameter, they will come together, right? If I have to say, think about this, okay? I want to group them together, right? And let's say these are the values. I want to group them together. All right. So a quickest way would be to sort this data. I'm sorting this data. So you can see that this data has been sorted now. Grouping is a matter of basically scanning from top to down only once. Okay. You can see that we can basically keep on grouping them together unless the two consecutive values are same. You can see that we have been able to group these many values while I was talking. So it's pretty straightforward. All right. Okay. Thank you, Mahesh, for that. Mahesh is saying, just a quick check. Are there anyone in the class need to know algorithm analysis? Is it needed or not? Okay. So algorithm analysis is generally for your what do you call back of the envelope calculation. Okay, back of the envelope calculation is that when you stumble upon a problem, when you see the data, generally, if you are scanning through the data in a big way, then it's going to be extremely slow. But if you are jumping around, or using a binary search, or using any of these techniques, it'll be faster. Okay, so is there anyone else in the class, is anyone in the class who needs to know algorithm analysis? In my opinion, knowing the general strategy of algorithm analysis is quite an important aspect. Mamta says, I would like to know. Okay, anybody else? All right, anybody else would like to know? Mahesh, yes, and Mamta, all three of you. And all right, all right, okay, okay. So, all right. So, yeah, first let me just finish this part. So, you can see that group by is nothing but sorting. If you sort the data, you can group it very quickly. Fifth, did we leave anything? Order by, joins, group by, where clause. So, almost yes, we have covered SQL query. So, you can see that. Now, you can see clearly that all of the SQL, the main parts of the SQL, revolve around sorting algorithm. The better the sorting algorithm, the faster will be your querying, and hence, the more are the chances that your database will be more uh, powerful and will be more easily adopted. Okay, so is everybody convinced how our database is impacted by sorting algorithm? All right. Now think about it. What happens when the data grows bigger and bigger? When the data grows bigger and bigger, sorting algorithm becomes slower, or any of the sorting techniques become really slow. Reason being the main problem with data is not the rate at which you can process it. Okay, it also turns out to be the rate at which we can read data. The disk and everything is very much slow. So that disk IO impacts everybody, including sorting algorithm. Now, if we could break down this sorting algorithm so that sorting can be done by hundreds of computers parallelly, we split the data on hundreds of computers, and then we can apply any all of these algorithms in parallel, right? If we could do the sorting of the data on the big data set using hundreds of computers, then we have largely solved our querying problem. We've largely solved our querying problem, and that's where Hadoop comes into play. Hadoop's MapReduce under the hood is nothing but a mammoth sorting engine, which basically sorts the data which has been already divided by HDFS. HDFS has already splitted the data and put the data in the cluster. And order by or sort by basically uh, sorry, the Hadoop has already broken the data by the way of HDFS into blocks and put it on multiple machines, right? Now, if we could just sort this data individually, or individually blocks of data we could sort, then our overall algorithm will be faster. Okay? So we will get back to this again in a minute. All right? So yes. So let me just. I hope you guys do not mind me discussing the complexity. I'll try to oversimplify at the risk of being a little too, maybe not too accurate. All right. I'll try to be simple than the okay, because these ideas are fairly simple. Okay. So let's talk about normal searching in the data. Okay. So I will say that there is a list of numbers. Say there is 2, there is 1, there is 45, there is 3, and there is again 2, and there is again 1. All right? And let's say that there are total number of n records. These are n records. All right? I'm talking about now the algorithm analysis. Okay? This sounds like really big problem, but if you look at it carefully, in the beginning, in most of the cases, it's nothing but counting numbers. Okay, so given n number of records, if you have to find a particular record, how many maximum hops it would require? If you have to find a particular number, let's say you're looking for 45. So what will you do is you will check 2, you will check 1, and then you will say, oh, this is where it is, right? And then let's say you are looking for 1, you will again start from the top and then keep on going, and then you will reach here, right? So for n records, how many hops will it take in worst case scenario? If there are n records in this list and you're looking for a particular value, how many maximum hops it would take? Mahesh, Yash, Mamta? Midili says n times. Okay, great. Yes, it will take n times. All right. So then we say that its complexity is n. Okay, its complexity is of the order of n, or we say O and n. Why is it doing that? Okay, so the complexity is of the order of n in this case. All right. Now, sounds good to you, everyone? Now, what if we have, what if we order this data? Okay, what if we order this data? Ordering this data could be many ways. One of the ways would be, let's just try to say, okay, one of the ways will be we pick up two, okay, okay, we pick up two and compare two with all other numbers, all right? Or, okay, so one of the ways is that we go over the list, whichever you find is smaller than two, you swap them, okay, you swap them, and then you keep on doing this swapping again and again, okay. So then you move ahead and then you see, okay, whichever is smaller, let it be there. Then you compare these two and then you swap them. Okay. Then you move ahead and then you compare these two and then you swap again. You swap again and then you keep on swapping this again. So, and again you reach to one, you swap these two. Okay. And then you again compare these two and you keep on swapping these numbers. Okay, you keep on swapping these numbers unless you reach to a situation. Now this data is sorted. If you think about it, again and again, if you think about it, the complexity that comes out to be is the order of n into n. Okay, n into n is the total number of comparison which is going to take in this case. Okay, so counting this is little too tricky. So in worst case scenario, the number of comparison will come out to be n into n. Okay, but if you use other algorithms such as quicksort or merge sort, what do we do in the quicksort? Okay, what we do in the quicksort? Uh, all right, I think I'll try to represent. Okay, so so in the these kind of scenarios, okay, in these kind of scenarios, what's happening is we are picking a particular record, we're comparing with all other records in the previous and inserting it at the place where it needs to be inserted. That is insertion sort, and the one which we I just demoed was a bubble sort. So in these bubble sort, insertion sort kind of a cases, the complexity turns out to be n into n or n square. Okay, so O n square is the order of complexity. Second is that let's talk about, say, quicksort. What happens in case of quicksort? All right, so or let's say merge sort, merge sort. All right. Now imagine that this is your search space or you have this data, okay, and let me try to represent data like this. Some bigger bar means bigger number and a smaller bar means a smaller number. Okay, you have this kind of data. All right, now In case of merge sort, we divide this into two sections. One this, two parts, and other this. Okay? And we keep on dividing it again and again. Unless the smallest division is two records. And then we basically merge it. Okay? So at the end of it, when you think about here, you will get two, as in kind of this kind of increasing list of values, and here also you will get increasing list of values. Okay, now this should look a little bigger. All right, so you'll have basically merge sort relies upon sorting two parts of the data independently and then merging them. When you have this two lists of values which are ordered, you can merge them easily. You pick up the front one from both the sides, and then you pick up the smaller one, and then you keep on doing it again and again. All right. So merging two data sets which are already ordered is very straightforward process. Okay. So merge sort keeps on dividing data, and then uh, and that division keeps on going downwards, keeps on going further and further unless we are left with two sets of records. Okay, unless we are left with two sets of record. If you want me to demonstrate to you here with this. Okay, so these are very clever algorithms. All right, so let's say there is this list which has 6 elements that needs to be sorted. Okay, we divided that list into two parts. One on the This is from 3 to 1, from 45 to and 1. Okay, now these are the two divisions. These are the two divisions, and let me just make it this way. Okay, this is the merge sort we are trying to do. So we have divided the list into two parts, one part and second part, without any particular order. We just said first half of the array goes is this side, second half that side. Now we further divide these data sets. Okay, we further divide this data set into two parts. Okay, and then we are left with this and this. Now sorting two records is very straightforward. Okay, so we sorted this data. Now we will merge these two records easily. We will basically compare this with the first value and then pick up the first value, and this we will pick up the first value. So we have merged these two records. Next is same thing will go on the other side. We will say let's break it into two parts and sort the two parts independently. Okay, and then we will merge these two. When you are merging these two, what would happen is compare the first one and this one. Okay, and whichever is smaller you pick up that one. Okay, and then then you compare this with the. Okay, so uh, all right, so I mean the way you can imagine merging the two queues is, think about standing in front of two queues of people where both the queues are in both the queues the students are standing in their increasing order of height, meaning the shortest one is just closer to you. You are facing the queue. Okay, so you are the sort of standing in front of the two queues facing the queues, and you're looking at the queues, and both the queues are already ordered. Okay, in both the queues people are standing by their increasing order of heights, right? Now, you as you have to merge these two queues into one. So you pick up the person who is in front, and out of that you pick up the smaller one, keep it aside, and then the out of the remaining list you again pick up the smaller one and then keep it put it into the output list. And that's what keeps on going when you merge two data set which are already sorted. Okay, now you can see that 1, 2, and 3, these need to be merged. So we come take 2 and 1, compare them, and pick up the smaller one out of it, and then we pick up the rest. Okay, so we have ordered the two data sets independently. Now we've got two data sets, one this and another this. We compare the front of these, and since they are equal, we pick them up and put it in the output. Okay, now we pick up the again we are left with these two one, and we compare the which one are is smaller. If they both are equal, we pick both of them and put it in the output. Then again pick the next one and compare it. So the 3 is smaller than 45, we pick 3 and then we pick 45. All right, so you can see that we have been able to order the data first in parts and then merging it together, and we could do it recursively, and this is called merge sort. This is probably the most used algorithm other than quicksort. All right, so if you think about it, it's basically of the order of I mean it be it will be little complex to compute it. So the order which comes out to be in case of merge sort order is n into log n. Okay. So if you have n number of records, the total number of comparisons, total number of times you have to compare elements will be around n into logarithm of n. All right, so this is something it will take a little more time to compute the order of the merge sort, but you can do a little bit of counting. This is essentially finding the order is counting how much time it takes to do something. Okay, how many comparisons it will take to do something. All right, so Basically, basically, we have been I've been trying to compute the order of various algorithms, and sorting the merge sort takes around n log n. The simply binary search takes around when you are just searching for searching for something in a list quickly. You can now again let me explain what does it mean by a binary search. Let's say you have to search for 2. Okay, you will go in the beginning. Okay, then you'll say, okay, my word which I'm looking for is greater than 1. Then you go in the end, you compare, or you don't go in the beginning. Let's say you just directly go to the last of the list, and then you compare whether the number I'm looking for is greater or smaller. If it is smaller, you go to the middle of it. Okay, when I say middle will be this particular one. We'll say the okay, or any of them. Okay, then you compare it and you will reach to the number which you are looking for. Okay, if you are looking for 3, you will basically first go to the maximum one, compare whether that number is bigger than 3 or smaller than 3. If it is bigger than 3, then you have to look into the only this one. So what you do is you look into the middle of it, and then see whether it's greater than 3 or lesser than 3. Now since 2 is lesser than 3, that means you have to search from here to here, right? And so you basically do the half of it, and then you will search. So basically, in case of binary search, you keep on hopping back and forward. Okay, unless you reach to your number. Okay, you keep on decreasing the search space by half every time. All right, did I make sense, everyone? All right. So basically, this is the general way of doing the what do you call the counting or doing the algorithm analysis. So most of the algorithm analysis is about counting number of times it takes to do certain operation. Okay, be it sorting, be it searching, be it ordering of things in the case of say forming a hierarchy and all of that. All right. So there are some more algorithms which are far more complex. Okay, I'll just give you an example of the probably the most complex algorithms. Okay, take a case of preparing hierarchy. Okay, take a case of preparing hierarchy. Imagine that you are given the details of n number of cars. Okay, you're given the details of n number of cars, and what you need to do is and compare these cars and form a hierarchy such as the cars which are similar to each other would appear next to each other. Okay, or you are given the details about the behavior of monkey, human, dog, fly, I would say eagle, cat, and butterfly. All right, and there could be, and there are there are such kind of list goes up to say 50,000 species. Okay, just only 50,000 species. All right, or n number of species, and you have to arrange them. You have to arrange them such that monkey monkey and human have the same parent. Okay, monkey and human has the same parent. All right, and then you have somewhere here as dog. Okay, dog and human, ha- dog and monkey. So basically we're preparing a hierarchy of the animals. Now, since human and monkey are closer to each other, and and you can say out of this hierarchy, you have cat and dog. I'll just try to draw cat and dog. Okay, so these they belong to kind of a same family. Okay, and then okay, so all right, so if you have to categorize the animals like this. Okay, this kind of algorithm, if there are n number of species, it will take around 2 to the power n. Or in this particular case of 50,000 species, it'll take 2 to the power 50,000. Okay, so these are the complex cases of algorithms. Okay, these algorithms are considered largely unsolvable. Okay, using a single computer. Okay, because not because the data is huge, but the kind of problem we are trying to solve is complex. Okay, the basically what Darwin did for us, what Darwin or other geologists did for us was something wonderful. They took the list of all the animals, they analyzed it, and then they prepared a hierarchy of animals by their behavior. And that kind of a problem, even if all of the data is available to us upfront, organizing them into a hierarchy automatically is as of today possible, but it takes a lot of time. Okay, so 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 that those algorithms are generally considered as the third V called variety. Okay, where your problem is far more complex than sorting algorithms. Sorting algorithms, they are very comparatively very fast. The algorithm which we just now talked about is takes a lot of time. As in, there are three or four different kinds of algorithm. One is around n cube, n into n, that many comparisons. So if you have 10 record, it will take 10,000 comparisons. If you have 100 records, it will take 100 into 100 into 100, that's a 1 million comparison. And if you have 1,000 records, it goes up to 1,000 into 1,000 into 1,000, which is 1 billion comparisons. Okay, so as the data is growing, the number of operations are growing at a very fast pace, and therefore it becomes impossible to do such kind of problems using even a single computer, using even a supercomputer. And that's where the quantum computing, or the that's where the big data computing is helping a lot. Okay, so big data computing is really boon for most of these complex problems. Okay, finding DNA structure and all of these are actually fairly complex problems. Their number of comparisons are very high. Okay, so on one hand, we have these number of comparisons, number of steps that it takes to solve a problem. On other hand, is the time it takes to read the data. Okay, sometimes the number of comparisons are less, but the amount of data is too huge. Okay, such as, let's say you have to grab a string in the volume of logs. Volume of logs as in, you have a nice website, you're pretty happy with the website, but and there are lots of users coming on the website, and you're maintaining the logs of all the users. Now, after 2 years of the logs, you have got around 2000 terabytes of data. Okay, and out of this 2000 terabyte of data, you're looking for a particular you're looking for a particular error message in the logs. Now, scanning 2000 terabytes data is very huge. Actually, when I say 2000 terabytes, is little overstatement. Yeah, but such kind of problem, even searching for a particular word, okay, will take a lot of time. Why? Because reading 1 terabyte data from the disk takes around 5000 seconds. Okay, it takes around 5000 seconds. Now, reading 2000 terabyte data is quite difficult by a single computer, because the disk IOs are very slow. And therefore, if you have multiple computers, you get first go- so many CPUs. The moment you Instead of one computer, if you have two computers, you got twice the disk IO, which means you can read at twice the speed from the disk. Second, you got twice the CPU. You can do number of comparisons twice, and you got twice the memory, and you got twice the network speed. Therefore, these big data computing and these are all of these computings help you in a lot of ways. And from the algorithm analysis point of view, you are able to split the number of comparisons or number of steps onto multiple computers in order to solve your problem really fast. Okay, so uh, that was a quick overview of probably the most important topic in computing about the analysis of algorithms. Okay, all right, all right. So, yes. So there are these kind of problems which are really difficult to solve easily. Now there's a point from Biswa, and the point is, if it is a binary tree, then this is the order. If it is not a binary tree, then it would be the same order. Yeah, if it is a binary tree, uh, yes, that's right. If it's a binary tree, then what he's suggesting is 2 to the power n. Yeah, okay. So there are two different algorithms which we talked about, classifying the people or classifying the elements into a tree. One takes around 2 to the power n, and other takes around n to the power 3. Okay, these many steps. And both have their own pros and cons. All right, coming back to it again. So whenever you stumble upon a problem in computing, whatever strategy you see, you should generally think about two aspects. First, how many number of steps will it take? Second, what kind of disk IO are we talking about? Okay, how much data and how much time will it take? So those are the two aspects of the problem solving you should look at. Every time you look at a computing problem, you should generally question that what kind of data are we talking here? Second, and when you think about what kind of data, you should think about two, three things. First, reading 1 GB of data from the disk is 5 seconds. Second, the if the data doesn't fit into the memory, it will have to be splitted. So does the strategy requires us to load all of the data into memory or not? All right. Next is next is the how many comparisons it takes. Okay. All right. Let me just digress a little bit more, and I have talked about this much. So there are three things. In one case, disk might be the disk might be the okay disk as the bottleneck. So bottlenecks in computing, bottlenecks in mostly in today's computing. Okay, so first you check whether how much data. Okay, and and keep this number in mind. 1 GB takes close to 5 seconds, even on the fastest disk. Okay, that is the disk as a bottleneck. Next is how much data again. Okay, RAMs are of the size of 32 GB in the production environment. Okay, so if your data which you're trying to load it into memory, okay, if the data you're trying to load it in the memory is bigger than 32 GB, the RAM might be the problem. Although there are machines in the servers, they go up to 200 GB. Okay, all right. Next is how many comparisons. Okay, how many comparisons. All right, and keep in mind that 1 million comparisons are okay. Basically, this is where the ON comes into play. Okay, if if something is bigger than n log n, if the number of records that you're trying to churn are bigger than n log n, then CPU will be the bottleneck, or or, or processor will be the bottleneck. All right. So So we talked about three things: processor, RAM, and disk. So every time you face a big data problem, these are the three things you should generally question. Okay? So first you look at the total amount of data and see how much data are we trying to process in overall. Okay? And on every GB, you should keep 5 seconds. Second, how much data is this particular algorithm keeping in memory? Okay. So these are basically quick way to keep the numbers ready so that your instinct can tell you easily that hey, this problem requires big data or not. All right. Coming back to it again. So we talked about why sorting is a bigger problem and how sorting can help you do a lot of things. The problem with the first algorithm, the strategy number one, approach number one, was we were trying to load data into the memory, right? In this strategy number one, we were basically trying to load everything into memory. Quickly, we will run out of memory and will not be able to use this problem. Second, Second problem was SQL kind of problem where we basically used SQL's way of managing data. All right. Now SQL manages data very well because when you do group by, it basically orders data and does the work. In the third approach, In the third approach, which is the Unix way, what are we going to do is we are going to take a file and we are basically going to use the Unix pipes to solve our problem. All right. What we're going to do is we are going to get the file, pipe the data to the SED command. SED command is stream editor, which means it can edit the incoming stream of the data. Okay, so and this is where the stream processing and whatnot started as the word. So we will, are we logged in? All right. So, so in this kind of, all right. So what does it do? It replaces space or tabs with new line. Slash n means new line, and expression, this expression means this expression means space or tab. So it says SED substitute space or tab with new line. Okay, with new line. That's what it does. All right. Now let me try to log in. All right. Let me try to give you demo of this part. All right. And once we have replaced space or tab with the new line, that means there will be one word per line. Then we are using a command called sort. What does sort do? Sort orders the input lines into an increasing or decreasing order. And what we have done here is we have said minus capital S 1G. What does it mean? It means use only 1 GB of memory. All right. Now, sort algorithm can break down the things into parts. You remember merge sort we just did? It basically did half and half. Okay. So it basically proved that if we have two sorted data, if we have 4 GB of data and we have split it into four parts and we sort these four parts, we can easily merge them together. Okay, that's what sort algorithm does. It splits the data into gigabytes and then merge it. Okay, merging sorted data is not a big challenge. Okay, is everybody clear on how the merging of sorted data would help? That will come again. All right, so let's try to solve this problem. Okay, let's try to do it right away. And that's the beauty of using Unix command, that you don't have inertia to solve a problem. Okay, so do we have big.txt here? Let me copy it to local. All right, right now these commands can only be used if the file is on your local machine, not in HDFS. Okay, or we could say Hadoop fs minus cat. Let me just copy it first. Copy to local. And what was the name of the file? Slash data slash mr slash word count slash inside word count. What was that folder name? Inside data mr word count input slash big.txt. And what I want to do is copy it to look current folder. Now when I say ls, it will appear now. You can see that this is my file which I want to sort. All right. In this, if you if you just put a more means you want to see what is there inside this incoming stream page by page. If you don't put more here, you'll get all the content of the big.txt on the screen. All right. Next thing you want to do is you want to replace you want to replace space you want to replace space with new line. Okay. Let's see if it is working. Again, I have put more so that I can get page wise. Otherwise, it'll be screen blindness. Screen blindness. We call it screen blindness when too much text is on the screen. All right. Now we have been able to convert spaces into new line. You can see one word per line. All right. Now, sometimes you may want to use translate. What does translate do? Translate basically converts the uppercase or translates the letters to any other range. So here we are converting it, the input stream into the lowercase. Okay, so all I'm trying to show you is how we can use piping to solve all our problems. Okay, now all our data related problems. So we have taken the big.txt, replaced space with the new line, and then replaced capitals with lowers, and then we are using command called sort. Okay. Now, if you don't specify, you can see that it's taking time. All right. These are blank lines. These are blank lines. All right. Now we can further give it to another command called unique. Okay, we can give it to unique, and unique minus c will give us the count of all the unique words in the input line. All right, you can see that it's showing the number in front of this. It's showing 114 has occurred 11 times. Okay, all right, makes sense to you. Now you see these special characters. You can go a further saying replace anything which is not alphanumeric, or okay, replace it with a space. All right, now you can see that, and we can basically take it further one more step and sort it by number of frequencies. Okay. And in case we want the more frequent one up, we can say this. You can see is the tab. I think there must be some tab or space that has come so many times, and the, of, and, to, and so on. You can see that it has find out that it's a basically English text where these common words are occurring quite often. Okay, so Atasa seems to be some kind of important person in the whole text because other it is coming at a at the top. Okay, so I'll just give you this command so it'll be useful to all of you. Mamta's question is why are we getting blank lines when replaced spaces? The answer to this lies in seeing this data. Okay, when you say cat big.txt, you can see the like so many blank lines are there. Between two paragraphs, there are so many blank lines. And this is what happens when you don't put more. You can see there are so many blank lines. Here, there are two blank lines here, one here, one here, one here, and so on. That's why we are getting blank lines. All right. So this approach, which is using Unix, here we are using one particular argument which stops us from making the RAM a bottleneck. The moment we say use sort minus S1G, it's going to only consume at most 1 gigabyte of RAM. Okay? Alright. So the folder name is, let me just give you this command. That'll be better. Alright. Yeah, you got it. Alright. Great. So we have been able to sort data using 1 gigabyte of RAM, and it can actually handle hundreds of gigabyte of data. Okay, the moment we split it, the only thing that'll be bottleneck if in 100 gigabyte data would be 5 into 100 seconds. That much time it will take minimum to read data and then write it back after sorting it. All right, so this was the second approach. All right, okay, so yes, Biswa, are you able to copy it? Let me just try to understand where are you stuck. Great. So everything is in peace now? All right. Abhay's question is, an ls on command prompt in my account doesn't give me any files. That's right, because you have not copied any file. And Abhay is saying, what disk does it refer to? Okay, you mean this command which I've sent to you, Hadoop fs copy to local, is basically this computer here. You see this one. Oh, where did it go? What happened to this? Looks like it has been killed. This computer here is essentially uh, this computer here is essentially e.cloudxlab.com. And when we say ls, we are talking about local file system, and when we say Hadoop fs minus ls, we are talking to hdfs. All right, hdfs as in there'll be name node, data node, and all that. Abhay, was I able to clarify? I'm not sure. Yes, e.cloudxlab.com. Yes, it's a machine name. And here, right now, we are inside that e.cloudxlab.com. This command prompt is running inside e.cloudxlab.com. All right. Abhay's question is, how can I copy files into this machine? I think you can refer to this particular manual, maybe on the second session. Okay, that should help you. If you have any problem, because we have discussed it already, I okay. So there'll be two steps. If you want to copy here any file, first you will have to put it in Hue and then do copy to local. All right. Through Hue, the files directly go into HDFS. All right. Great. Great. All right. Now, in the approach number 2 and 3, I think we have already discussed this part, but I would like to again ask you. Yes, there is an upload option in Hue. Okay, have a look on the towards the right hand side. You go to the file browser, and then you will see a button towards the right hand side called upload. Okay, Mahesh, could you send me the screenshot? All right, let me take a look. All right, now going back here again, so I'll show you this in case you get confused. So here you go to the file browser. Okay, there in file browser you will see these folders. Okay, these folders, this is HDFS. On the towards the right top side you can see upload files. All right, so Mahesh, are you not able to see this upload button here, or you're not able to see this entire file browser? All right, great. All right, moving on. Great, he's able to see. All right, so right now, my question to all of you, these two approaches, one is of SQL and other is of Unix. Okay, what is wrong with them? Will there be a situation where you won't be able to use them efficiently? Will it get stuck? So, of course, there is no memory bottleneck as compared to this. The approach number one. In approach number one, we were having the memory as the bottleneck, where we were loading everything into memory. But in case of SQL, SQL takes care of the memory bottlenecks. Okay. Similarly, our Unix command has taken care of the memory bottleneck by using an option called minus capital S1G. So question to all of you is, what is wrong with approach number 2 and 3, the SQL and the Unix approach? Anyone? Okay, Mahesh is saying SQL has got data size limits. Good, keep going. Out of the three things which we just discussed, disk, RAM, and CPU, can there be a situation that any of those three become the bottleneck? Imagine that the data is growing further and further, okay, and you have say 200 gigabytes of data or 500 gigabytes of data or 1 terabyte of data. What would happen to the approach number 2 and approach number 3? Will there be something which will get become the bottleneck? Mahesh says that it will be the processor. Yes says lot of paging will happen. Good, brilliant, keep going. Discontention will happen in SQL. Brilliant, brilliant. Yes. So in both these cases, what will become the bottleneck, approach number 2 and approach number 3, is not the memory anymore. It is the disk. It is the disk that will become the bottleneck. Okay. So the moment data starts going beyond RAM, the disk as well as CPU will become the bottleneck. Okay, CPU in the sense that it has to do a lot of work in sorting so much data and reading writing into the disk and so on. Therefore, first the disk speed and then disk space and then CPU will become the bottleneck. And that is where the story of big data begins. Up to approach number 3, we were all happy, okay, so far. Okay, we had been able to successfully do these operations happily so far, as long as the approach number 2 and 3 do not become impossible to use. Okay, and that's where the story of big data begins, because the disk has become this bottleneck and CPU is also going to become bottleneck as the data grows. Now, what options do we have? What can we do to make it possible to find out the word frequencies in 1 terabyte data? What options do we have? Okay, all right. So, one of the suggestions is let's use hundreds of computers in parallel or multiple computers in parallel. Imagine that the input data is sa, re, ga, ga, re. Okay, so one part of the data we send to machine 1, one part of the data we send it to machine 2. Let machine 1 and machine 2 do the word count for you, and then you gather the statistics from machine 1 and machine 2 and then combine them into a single statistics. Okay, okay, the way we did the merge sort, in the same way you will do the merging of the frequency list sent by machine 1 and machine 2 to you. Okay, so what do you see here? Yes, both of you are right, Biswa and Yes, brilliant. Biswa says divide the file into smaller ones, and Yes says execute merge sort on many machines. Exactly, that is our approach number 4. In this approach number 4, this launcher, that's where you're sitting on this launcher and you have sent half of the data to machine 1, half of the data to machine 2. This launcher could be any of the machine 1 or machine 2 as well. Just for the representation purposes, we have kept you outside the system. Now you have got two machine 1, machine 2, and you have given them half of work and let them do the processing and give you the result. Like the first machine will say I got ray twice and second and sa as one, you can see, out of sa ray. And here machine 2 say I got ga 2 and ray 1. Also please note here, ray is above than the sa in this list, ga is above the, meaning machine 1 and machine 2 is returning the frequencies in ordered way, in sequential way, or in sorted way, so that you as the launcher can merge them quickly. Imagine that machine 1 and machine 2 did not give you these lists in ordered way. Then you again have to order this data and then merge, and that will be again a big problem. So machine 1 and machine 2, you have coded in such a way that they do your work, and once they're done, they give you the results back. Okay? And then you, who is sitting on the launcher, will merge these two statistics together, and then will present it to the user. Okay? Now, the approach number 3 or 2 is being used in machine 1 and machine 2 independently. Okay, 3 and 2 both are being used in machine 1 and machine 2 independently, and then on the launcher you are aggregating the results. On the launcher you split it the work, let machine 1 and machine 2 use either of the approaches out of approach number 2 and approach number 3, Unix or SQL way, and then you are merging it. Now you're getting this result. So do you find anything wrong with this? Do you find anything wrong with this? What exactly is the problem with approach number 2, approach number 4? This is approach number 4. This is also known as external sort. Okay, this is external sort. Okay, so what exactly? All right. So Abhay and Biswa, I'll answer to your question after this. All right. Let's just try to go with this. All right. So is this approach clear to everyone? We are dividing the work amongst multiple machines. Okay. We forget about yarn for a moment. We are dividing work. Let's imagine that this is some kind of a new system. We are dividing work by ourselves, giving it to machine 1 and machine 2, and let machine 1 and machine 2 use either of the SQL or Unix way of doing the sorting, and then get back to you with the results. Now, and you sitting on the launcher will combine the results and put it in the output. What exactly is wrong with the approach number 4? All right, let's take a break and discuss it after the break. There are two more questions I need to address that I'll do it after the break. All right, break for 10 minutes and back by 8:41 a.m. IST. All right, so I'm back. Should we start now? All right. All right, one more important announcement to all of you. Here, just if you have any questions, drop an email to Hadoop at No Big Data. Reach us is generally taken care by the salespeople, the other person who takes care of general inquiries. The technical questions are generally looked in by me. So send me an email at Hadoop at No Big Data. And Lakshmi's question was that she had tried to send us an email and she hasn't got response. So I've looked into it. I'll reply to you quickly. I just looked into it. Just that any question you have, drop me at email at Hadoop at No Big Data. All right, all of you. All right. Okay, so let me put these questions here. One was from Biswa. All right. Okay, so coming back to the questions. The problems with approach number 4. We were talking about the problems with approach number 4. We are using multiple machines to solve our problem. Okay. All right. So that is Lakshmi. I'll just make a to do for me. Okay. All right. Yes. So from Midili, the point was the approach number 2 is time consuming. That's correct. Splitting of data could be a problem. That's right. In this, if you have these two machines, you are taking data from launcher to machine, and that could be time consuming. What else? Mahesh says memory of the launcher could be a problem. Okay, okay. Yes, that's a very important point. So launcher who is collecting data from all the places, from multiple machines, even though it's getting work done using multiple machines, if if data is too high, launcher could be a problem. But in this case, when it's merging these two lists, it doesn't have to keep these in memory because it doesn't need all of it immediately. It can simply read these two files, okay, sequentially one at a time, from top to bottom, and then merge it. So it doesn't need to load these two files in the memory. Okay. Which is saying local resource manager and network are in question now. Yes, that's correct. That's correct. Keep going. Yeah. You guys are actually giving very good answers. So, what else do you see a problem in this approach? We talked about earlier approach number 1, where RAM was a problem, approach number 2 and 3, where CPU or the disk IO would be the problem, and now the approach number 4, whereby we have divided data into chunks and the work is getting done by multiple machines instead of one. So launcher is sending this data to machine 1, launcher is sending the other parts to machine 2, and so on. Yes, anyone? Mamta says I/O could be a problem. Yes, that's right. For launcher, the I/O will be a problem. Network I/O specifically, because this data has to be sent over the network. That's right. Good. Brilliant. Now, there are many many issues with this approach number 4. First problem with this approach number 4 is there's a lot of time is being consumed in transport of the data. All right? A lot of time is being consumed in the transport of the data, and for each requirement, we need a special purpose network oriented program. Now, right now, we try to solve the word count problem. Tomorrow, we might have another sorting problem or another kind of problem. Then again, we have to reprogram everything. Okay? Third is there's a lot of work required in terms of engineering. What if things fail? What if machine number 1 fails? Then we have to schedule the same work at machine number 3. Similarly, if we have to make it scalable, from time to time we have to keep on adding machines. Okay, we'll have to update the whole system. All right, imagine having 100 machines and adding one more machine, 101th machine. Then the whole ecosystem need to be informed that we have got 101 machine. Now the way you are dividing your work can be done further. So there are a lot of mechanics required in these cases. So there are these three problems. There are these three problems these three problems. One is lot of time consumed in the transport of data, and for each requirement, we'll have to create custom solutions. Third, it would require a lot of engineering in terms of failover, scaling up, and backup. Okay, so that's where the MapReduce comes into play. Okay, Hadoop MapReduce comes into play. How does it solve the first problem? In HDFS, data is already transported to machine 1 and machine 2. It's already divided and transported to machine 1 and machine 2. So you don't need to transport the data. Here in our example, approach number 4, we were dividing the data and then transferring the data to both the nodes. Okay? And that's how the approach number 4 was working. But in case of HDFS, in case of Hadoop, the data is already spread across the network, right? Remember the data blocks, remember the data node, remember the name node. So the data was already transported to the data. So transported to all the machines. So that is the first problem of approach number 4 being solved by Hadoop. Second, for each requirement, we need to stitch the custom solution. And that's where the MapReduce comes into play. All you need to write is this small, nice piece of code called map and reduce. And you don't have to do the whole engineering. You can simply write this small piece of code, which is a very small amount of work that you need to do, okay, as compared to the whole engineering. Like in the approach number 4, there's a lot of engineering. Like split this data into two half, send it to two machines, get it done, run this program on this machine, run that program on that machine, and that whole program has to be written by you, and then get the work back, and then do the merging and do all of that magic. Okay, so for each program we have to write this thing. Instead of that, what if we had something like a MapReduce, which does everything. The Hadoop MapReduce takes maps and reduce logic from you, execute it, and give it back to you. All right, and that's how that's how it works. Okay, so second problem is also very well solved by Hadoop MapReduce. Third, a lot of engineering. We talked about Yarn. Yarn takes care of the failover. Yarn makes sure Yarn can execute anything for you in the network. So, using Yarn and Hadoop MapReduce paradigm, we are able to avoid all these three problems very well. Okay, we are able to avoid all these three problems very well, and that's why we use Hadoop MapReduce. As we go forward, you will understand more why these three problems are being very well solved by Hadoop MapReduce. So now we have set up the basic reasoning behind Hadoop MapReduce. Okay, so Was I able to convince you that Hadoop MapReduce is in fact a good solution? All right. All right. As we go forward, we will try more and more and then try to see what else could be done in order to solve such kind of problems. All right. Now there are a few questions I need to answer. Can we revisit yesterday's slide for App Master to depict the role of launcher? Yes, we could have done that. So, all right, here, when we are dividing the work here, it is similar to what we discussed yesterday. Okay, it's similar to what we discussed yesterday. Okay, this resource manager giving work to all these nodes to get it done. Okay, in the similar way, in the approach number 4, we were trying to do the same thing, meaning we were trying to build our own on the similar lines. All right. Good, good. Next is, do I need to be conversant with Unix? Honestly, it'll be great if you basically go through basics of Unix. Know how is the folder structure is uh, how is the folder structure, then know what are the basic commands and know how to filter, how to use the pipes in case of Unix. Okay, that should be more than enough. If you understand filters or pipes, you will be very comfortable. All right, so that's where the MapReduce comes in. All right, now, all right, so what exactly is MapReduce? First, it's a programming paradigm. MapReduce has been into existence even before Hadoop came into play, even before even before Google published its paper. The MapReduce is a keyword for translating, basically running a logic over a lot of data. Okay, that has been, so if you have an array and you want to process each element of the array, and without looping you can run the map function. Okay, if you want to summarize the whole array into a single value, you can use the reduce function. And that's how MapReduce has been looked upon since the days of what do you call functional programming. So I have used long back the MapReduce while I was coding in Perl in 2001, and at that point of time, the the connotation of MapReduce was in order to simplify our problem. Okay, so MapReduce is a programming paradigm in Hadoop MapReduce specifically. Here we are talking about Hadoop MapReduce. Hadoop MapReduce is to help you solve big data problems, specifically those problems which are sorting intensive. If your problem has to do a lot of sorting, then Hadoop MapReduce is good for you. You would have to code two functions. One is mapper, other is reducer. Mapper, in mapper, you will write the logic what has to be done on each individual node. Okay, a logic which takes an input line and converts it into key value pair. This mapper is responsible for deciding on what basis the data need to be sorted. The role of the mapper is to decide on what basis do we need to sort the data. Okay, meaning it has to give key value pair where key is the thing on the basis of which the data will be grouped together. So overall objective of Hadoop MapReduce is to group the data. Hadoop MapReduce groups the data by key. And now who defines that key? It is the map function of yours which will convert each record into key value. Now that key value will be taken by Hadoop from your program, and then the data will be ordered, grouped together. by that key. All right. Again, let me take a step back. So when you think about Hadoop MapReduce, think it in this way: that Hadoop MapReduce, all it does is it groups the data. Now, when we say grouping the data, it means it there's somebody who needs to say that, okay, this is my data, this is my data, and this is the column on which it needs to be grouped. Okay, and that's what it done by your map function. Given an individual record, your map function has to tell that this is my key and this is my value. The key is the one on the basis of which you will group the data. The key is the one on the basis of which Hadoop will group the data. So role of mapper is to convert input lines into key value so that Hadoop can sort the data by that key. Okay, Hadoop MR can do that. Next, you will have to write reducer. Okay, now we have said, okay, group our data. It will group our data by key. Hadoop will take these key value k1, k2, k3, k4 and so on, and then group all the values for each key together. Now we got a list of values. How do those values be combined? That is done using your reducer. That is done using your reducer. Okay? All right. Now MapReduce as a paradigm is supported by many systems such as MongoDB, CouchDB, Cassandra, Apache Spark. All right. Map and reduce in Hadoop can also be written in Java, Shell, Python, or any binary for that matter. Okay. All right. Let's try to see what happens. So one is word count problem. I think we should pick up a simpler one first. Okay. Let me pick up simpler one. All right. I'll pick up a simpler one. All right. Imagine there is a class. Okay. In this class, there is a student name, and we have marks. Okay. And there is one more, we call it subject. Okay. So we have got student name, subject, and marks. So student name is A, then followed by a tab. Subject is, say, subject 1, and marks is 10. For the same student, in second subject, you've got 20 marks. And for another student in S1, you have got 30 marks. And B in S3. Okay? Alright. Now, this is written in a file. Okay, this is written in file where each row is splitted by tab. Now, let's say your objective is find the total marks of a student. Okay. Also note that it is not compulsory that A's marks come always together. It could have been something of this sort. Okay. Now you have to find out every student marks, and this data is written in a file. All right. Okay. So what will be? So this data, when we launch our MapReduce process, we will tell Hadoop that this is our input file, and then we will also hand over map function. Our map function is supposed to find out the key and value, is supposed to give out the key and value. All right. So question here is you have to find the total marks of each student. Of each student. All right, anybody? Okay, so this is, let's say I call it class.txt. This is your file name, okay, in which this data is saved in this way. There is no header. Okay, I just want to mention that that there is no header. Okay, now, okay, i'll repeat the question I'll repeat the question for you. Question is, you are given this text file called class.txt, which contains three columns: student name, subject, and marks. Now, what you need to do is you have to find out the total marks of each student using MapReduce. So, to Hadoop MapReduce, we will give class.txt. Okay, and in the class.txt, we will also we will give class.txt as the input, and then we will give map and reduce function. Map is supposed to convert this into key value pair. Had it been our database table, it could have been very straightforward. All it requires is group by student name and sum the marks, right? Which means aggregation is summation and group by is on A. Therefore, in the same way, map will give out when this data is given to map will give out the A and 10, B and 40, and and C and 10, B and 30, A and 20. So map will give out this result. So you will write the code in map such that it picks up line by it will it will convert the input line into this output. Also, please note that inside map you do not have to iterate over data. You are given the input line and you have to convert this. If I have to write the pseudocode, the map function will look like this. Line is the argument here, and all we are doing is return $0, okay, or we can say line dot split, and we are saying line dot split. We can say my array equals to line dot split. We have split the line, and we are saying return array 0 comma array 2. We are skipping the second column. So this is all map function looks like. All right. Now, once map produces the key value pair in this way, Hadoop will take all of this, gather all of this, and then combine and then order it. Okay. Now Hadoop will take. So this is your map function. Map function has converted this output. Hadoop will take this and order this. Okay, let me order it. Okay, so Hadoop will convert this data which is given in the previous screen into something of this. Now you can see that Hadoop has sorted the data by key value. Next step Hadoop will do is it will feed this data per key. Okay, it will sort it, and then next thing it will do is it will group the data together. It'll group the data together like this. Okay, and now for each key, all right, you can also make a pictorial diagram here also. For each of this function, our map function is being called for each of the row in the data. Okay, the same way, like this. All right, and we are getting this value. All right, so that's what is happening. And for each of the data that is here, each of the key, it is going to be passed to our reduce function. Whatever reduce function you define, that function is going to be called on each of the key and all the values of that key. Okay, Imagine that your reduce function looks like this. Okay, key, comma, list of values. Okay, and all it does is it returns key, it returns key, comma, summation of list of values. Okay, it's a pseudocode. Now, and that's where it'll look like this. It'll look like a a space 30, b space 70, and c space 10. Okay, makes sense to you? No? All right. So yes, most of you are correct when you say that key will be student name. That's right, Mahesh. Okay, that's right, Mamta. Sort based on student name. Similarly, Biswa also sort based on student name, and then sum based on each group. Okay. Key is the student name. Value is the total marks for the map. Yes. Okay. Now, Mahesh's question is, where does this data go? It will store in the HDFS. Okay, all these results will go into HDFS. All right, Mahesh's question is, how does Hadoop know it has to sort? So in Hadoop, we by default, the output of map, this output produced by map, Hadoop assumes that you have to sort that output. Okay, and based on the key given by your map, because Hadoop MapReduce is nothing but a big sorting system. It sorts the data, that's all it does. All right. Now question from Mahesh is interesting. He says that where is the result? So one question was, this output of reduce, is it going to be stored on the same machine or different machine? Okay. Okay, the answer is that it goes to HDFS, and the way HDFS works is the first copy of the data is stored on the same machine from which you are executing command. Okay, because you are in a Hadoop cluster. So wherever the reduce is being done, wherever the reduce function is being executed on the same machine, the Hadoop will be storing the first copy in HDFS. All right, there is a question from Abhay. Question is, are we going to get this text file only in such format as input to the MapReduce? Answer is no. Okay, so here in whatever format the data is, it'll be given to your map. There are many ways, there could be many input format. We will talk about something called input format. Here, by default, we are using a mechanism, an input format called text input format. In text input format, if a text file is given, its each line will be fed to your mapper function. Each line will be fed to your mapper function, and then mapper would be expected to give us the key and the value. Give to the Hadoop. Mapper will be expected to give to the Hadoop the key and the value. And based on that key and the value, Hadoop will gather such kind of key values on all of the data. And please note that it's not you who is executing map. It is Hadoop who is executing your map. You basically handed over your piece of code written in the form of maps and reduces. So you wrote a function called map, you wrote a function called reduce, and you told Hadoop that, hey, here is my map function, here is my reduce function, and this is the input file. Now do the magic. And Hadoop will read this input text file called class.txt. And then for each line of that file, Hadoop is going to run your map function, and your map function will be expected to give key values to Hadoop. And then Hadoop will gather all those key values, and after gathering those key values, it will give it to the reduce function. Now question is, what is so big deal? How does it help our problem? The thing is, this map function will be executed on many machines in parallel. Okay, wherever the parts of text file are existing in your cluster. So cluster.txt file will, if it is spread across 50 blocks, okay, so, and these 50 blocks are in 50 different computers. So parallelly on each computer, map function is going to be executed against each line. Okay, if there are a billion line in class.txt file, if there are billion line in class.txt file, then map function is going to be executed a billion times. Okay, and in case and this will happen on all the machine in which these 1 billion lines are spread across. Okay, so on each computer in the network, the on each computer in the network, on each line of the input text, your map function is going to get executed. You will code your map function, and you don't have to worry about the dynamics of Hadoop while writing map function. All you have to worry is, what is that logic that will convert input line into key value? What should be my criteria for preparing the input key? Okay, you could do the lowercase of a, or you could also do other kind of things while preparing key. In case of map and reduce is proper programming language. You can write anything you want inside map function. Imagine this, let's say for each student name you have to look up in a database, and you have to find their registered number. Okay, and then you want to make that as the key. You can do all that. You can do anything a programming language such as Java can do. All right, next question from Mahesh is that, does it do the replication of the result? Yes, of course. The output is just another HDFS file, therefore it will do the replication. All right, I think uh, all right, so Mamta, I think I've answered exactly your question at the same time, right? All right, now let me try to give you another example of word count. Okay, let's have a look at this diagram. That will help you. Midili's question is, for text it works well, but how about audio and video as input? Because big data could be of any form. That's a very important point. All right, okay, so there is something called input record. Okay, so input record is prepared out of the input file. And this input record in our case right now is a plain text one. Tomorrow, if we have audio file, then we can break down audio file into input record, a set of smaller record. Okay, and we will discuss all of these details at a later point of time. How to handle JSON file, how to handle XML file, how to handle audio file, or we will discuss all of this. There's something called input format, and using input format you can handle every kind of data. You convert the big file into a set of input record. You have these input formatters, they convert the input big file into input records, and for each input record, your map function will be called. Right now, in case of text input format, the input record is a single line. All right. If you are processing data from HBase, the input record will be a single row from the database table. All right. Brilliant set of questions. Now, Mahesh's question is the reducer executed on each node too? No. Since reducer need to aggregate data, it is executed generally on a different node, gathering the data from multiple nodes on which maps are running. We'll show you this. All right? All right. No worries. So, Mahesh, as we go forward, you will see your answer going up. Yes, I would don't want to answer that Python and Scala question right now. Otherwise, it'll be ever-going war of the programming languages. But honestly, right now, the easiest thing to do is go with Python, and let's stick with that. Okay, I can have an offline discussion if you want regarding which programming language to go with. Okay, right now you can go with Python. Python is good. It would not take consume too much of time. All right. Because programming languages discussion is generally like a political warfare. All right, good, good. Now let's take another example, the same example where we are given these words in the form of sa, re, saga, and we have to find out the frequency of each word. Okay, so our map function will look like this. For each input word in input, print word comma 1. Okay, print word comma 1, and then Hadoop will take this output produced by map. Your map function produced so many key values for each line. For each line of the input, your map function producing so many lines, they are taken away by Hadoop and grouped like this. And once grouping happened, then on each group, on each group, reduce function is going to be executed. And this is what it is. You get the result. All right. Sometimes your data is huge. Then same map function will be taken to multiple machines. If your data is located on multiple machine, if your data has got two blocks, then the data will be taken, your logic will be taken to multiple machines, and there it will be executed, and the result will be gathered together by the way of merging, and afterwards the data will be saved into the disk. Okay, you can say that on one machine and on the second machine, you can see everywhere the point I have marked the pointers. On the node 1, the input data is sa, re, saga. On the node 2, the input data is sa, re, sa. Just for representation purposes, imagine you have got two blocks on two different machines, and you are trying to run MapReduce. On each machine, the map function is going to get executed. Your same function will be cloned twice, and will be executed parallelly on these two machines. Okay, here you have got this input at both the points. Then at the 2 point here, what you got is unordered data produced by map function. Okay, if there are 100 lines, then your map function here will be called 100 times. If there are 200 lines here, it will be called 200 times here. That means the total number of records will be 300 as a result of both execution of maps. So 2 and 2. And then the data will be sorted by Hadoop individually on node 1 and node 2, and you get this result. You can see that the data has resulted in this. Next is that once you are done with Once you are done with sorting, then the data will be merged and the output will be passed through the reduce function. Okay, and and while merging, as we talked about it earlier, since the data is sorted from both the sides, it'll be easy to merge. Okay, it'll be easy to merge. So for example, uh, 3 here and 3 here, you can see there are two lists of things. So out of this, first the smaller one will be picked, that goes in the output. Then ray and ray from both the sides will be combined together, and then sa from here and sa from here will be combined together. You will get this kind of groups. And afterwards, reduce will take these groups and say run run reduce function. Hadoop will take these groups, and for each group reduce will be executed. And what is it that reduce is doing here? Reduce is basically computing the sum of the array, which means gov1, ray2, and sa4. Okay, this is how the map reduce works. Next is, all right. Yes, Mahesh, that's correct. That's a right assumption. His point is that based on this picture, sorting and merging are executed by Hadoop without any coding by developer. That's correct. So these blocks are being done by Hadoop for you. Okay, these blocks are being done by her. Only code you have written is this map function and this reduce function, these two pieces of code. You can see that this is the only code you have written. You have not written any code which will do the sorting for you. Okay, very good question, Mahesh. Mahesh's question is this intermediate result of Hadoop at this stage is like at 2 this is the result, at 2 this is the result, at 3. So do you think it will be stored in HDFS? Any suggestions, anybody? Question is so intermediate results from this step 2, 3, and 4 are stored in HDFS. How long it will be in HDFS? Can anybody give the answer? Any guess? I'm not looking for correct answer. Biswa says yes. Mahesh says yes. But why? Why do you need these intermediate results in HDFS? All right. Yes. Because further question would arise that if yes, then for how long do we need to keep the results? Because these results are obsolete. The moment the process finishes, this result is obsolete. Then why do you want to take such a headache of transporting all of this data to HDFS and keep a copy of it there? Because every time you store something on HDFS, it's going to make 3 copies of it. So Mahesh's question is because Hadoop has to merge data from all the nodes into a single place. Very good point, but that's not good enough reason to keep it in HDFS. Biswas is saying because they are in pipeline of process. All right. So the answer is that the intermediate results are not stored in HDFS. Okay, are not stored in HDFS because these intermediate results are going to disappear anyway by the end of the process. Okay, therefore, it's not worth the effort to take care of to store it in HDFS. It'll take more time and it will also consume more space. Therefore, it is not worth keeping these intermediate results in HDFS. Instead, the local disks need will be used. Very good points. All right, let me show you another diagram depicting the behavior of MapReduce. Okay, let me try to explain what is going on. So there is a huge file which has got 3 blocks of data, And those three blocks are loaded in split 0, split 1, and split 2. Okay? Each block of data might be containing multiple records or multiple lines. Okay? Hundreds of thousands of lines or millions of lines for that matter. Now, what you see here is that there are three blocks of data loaded into a logical format called split. We'll talk about the difference between input split and input block. Right now, let's just assume that input split is similar to input block. You can say that input split is a wrapper over in the data block. Okay, just that the input split is part of Hadoop, data block is part of the HDFS. So on each data block, Hadoop will load each of the data block into input split, and on the input split, it will run map function. On each record of the input split, it is going to run map function against each record, and whatever is the result, it sorts it, and after sorting it saves it in the disk. Okay, split 1, split 2, split 0, all three broken down into records, and every record being passed through map function. Here you can see here that the input data is being passed through map function, and map is producing key and value, meaning the data and the criteria on which it need to be grouped. Okay, so map is producing key and the values, and that key values get sorted and put it into these boxes, and then all these boxes are carried to a central place and merged together, and after merging, then it executes your reduce function on each key and all its values. Why? Because why it's doing it here? Because for a same key could exist on this split, same key could exist this here or here. So all the keys from everywhere are gathered here. Okay, and for each key and all its values which have been grouped by Hadoop for you, are your reduce function is passed through it. So grouping and all of this process is being done by Hadoop for you. Hadoop MapReduce framework part. Okay, all you have to do is write map and reduce function. That's all. Where your map convert the input record into key value, and reduce combines all the values for each key. All right. So this diagram would make it very clear as in how MapReduce gets executed in the network. All right. Lakshmi's question is, can you please explain MapReduce in yarn architecture that you showed yesterday? All right. All right. I will come back to that again. Let me just finish up this part, because if I bring in the yarn architecture, it is going to be a little complex right now. Okay. All right. A question from Midley. So number of mappers is equal to number of splits. That's correct. So your map class or your map function will be loaded on each node per input split, and each input split might be having thousands of records. So each record is being passed through map function. So while the total number of instances of map function will be equal to the number of splits, but the execution of map will be equal to the total number of records. Okay, so one big file might be split into two big files, but our map function will be executed on each line. Correct? That's a little distinction. So another question from Mamta and Biswas. So that means the intermediate results are stored in outside the ecosystem. They're stored on the local file system. Okay, these results after map has finished, this result which is being fed to, so after sorting there is another result, before sorting there'll be another result, after sorting the data gets copied, so on. So all these intermediate data is on the local disk. Okay, kind of, yes. So the intermediate results will be on the same node as HDFS block is because map function will be executed nearer to the data. Okay, nearer to the data. All right. The very good question from Mahesh. What is the criteria for a record for Hadoop? Is it always line or we can define it? We can define it. This is what we call it custom input format. Biswa's question is, if a file is divided into many blocks and one node has few blocks, then how many mappers will execute on that node? Okay, if one single node is having multiple blocks, then there will be multiple instances of the mapper on the same machine. Okay, multiple instances on the same machine. All right. A very good question from Yash. Can we apply MapReduce for all kinds of scenarios? The answer is no, we cannot. All right, we cannot apply MapReduce for all kinds of scenarios. We will talk about it after some time. Mahesh's further question is same as what Midhili is asking. Is it one to one for each block to mapper? So kind of yes. Okay, the one to one is between input split and map. Okay, and generally input split is equivalent of input block, and therefore one map instance will be generally equal to number of in map instances will be equal to number of splits, and number of splits will generally be equal to the number of blocks. Okay, make sense to you? All right. In the same way, what if we have multiple data? This diagram is better. Okay. What if we have multiple reduces? Okay. What if we have multiple reduces? What would happen then? What would happen then is that this map function will put the data in two buckets. It will be decided all the words which are up to j will be kept in first bucket, and all the values after j will be in the second bucket, and first bucket will be carried to first reducer, second bucket will be carried to second reducer. So map will basically put the data into these two buckets based on certain arbitrary criteria. We will define something called combiner is responsible for splitting the output of map and putting that into these two buckets. So everywhere, node 1, node 2, node 3, there'll be two buckets produced on each output. And first bucket will be taken to first reducer, second bucket will be taken to second reducer. What are we talking about? We are talking about the what happens in the case where we have multiple reducers. Some of you have already asked this question to me. What will we do when we have multiple reducer? This is what goes on. If there are three buckets here, there'll be three buckets here. Okay, and one bucket for each reducer, and this bucket will be carried onto that reducer and so on. So you have input split block. That input split block get converted into key value pairs by the use of map function, and this map function produces keys and values, and these keys and values are kept in these two buckets, and these two buckets, one is carried to the first reducer and second is carried to the second reducer and so on. All right. Now, question from Mahesh is very good question, and these questions should be recorded. So, what is the criteria for multiple reducer? You define it. It is up to you how many reducer do you want. And we will talk about how do you decide number of reducers at a later point of time. Okay? If you have multiple reducers, you have multiple transport of data. If you have multiple reducers, you will have less headache on one node. If you have less number of reducers, the overload load on a single machine will be higher. Therefore, sometimes you have to go with multiple reducers. Next question from Mahesh is, does multiple reducers the same process code or each one is different? It's the same piece of code. You write it once, Hadoop runs at many places. Okay? Now, question is who manages these buckets? That's the question. So basically, Hadoop decides by itself based on number of reducers. It creates bucket. It creates like bags that okay, the first bag will go to this first reducer, second bag will go to the second reducer, and so on. Had there been 20 reducers in this case, our output of map will be divided into 20 buckets. Okay, and the logic to split this is based on separating the keys because map will be giving out the keys. For some keys will go into one bucket, some keys will go into another bucket, and so on. Next question from Idili is, are we deciding which output of mapper has to go to which reducer, or how Hadoop is deciding that. Okay, Hadoop is deciding that. All right. A question from Mahesh is, what if we want to combine part 0 and part 1 here? This part 0 and part 1. Do I need a different reducer? Is it possible? You can simply use concatenate command to do that. Okay? You can simply use concatenate command to do that. If if this data, the way you concatenate, is not something you wanted, what you can do is you can write your own MapReduce as a second phase to combine these results. All right. So you can see that the MapReduce is very much like group by, where we say, all right, where we say select word comma count star from a table group by the word. Okay, we are grouping the data by word and then counting all the values for each word. All right, so we define a function map where for each word in the input you print word comma 1. Okay, so here you can see that this part where we are saying that group by word, this portion of the data is here. Okay, second part which is reduce is equivalent to the aggregation. So column selection of group by is equivalent to defining the map function, while aggregation is similar to reduce function. Okay, I hope everybody is with me with analogies to group by syntax. Group by is SQL syntax to group the records by a certain criteria and then aggregating them. All right, is everyone with me? All right, brilliant. So looks like everyone is with me. All right, next question. All right, a question from Biswa, which is a very important question. In the previous slide here, we had part 0 and part 1. Okay, part 0 and part 1. So keys will not be repeated. If a key exists in part 0, it won't be in part 1. If a key is there in part 1, it won't be in part 0. Why? Because the same keys have been gathered onto the same node. Okay, therefore keys will not be repeated. All right, but the range may be overlapping, meaning meaning imagine you have this data. You have apple, apricot, bat, boy, cat, cow. Okay, so chances are that apple is on one machine, apricot is on another machine, bat is on one machine, boy is on another, and cow is on another. So maybe first reducer gives us that apple has occurred 10 times, bat has occurred 2 times, cat has occurred 45 times in our input text, apricot has occurred 10 times, and this has occurred 1000 times, this has occurred this many times. Although the output of each reducer will be ordered individually. The output of each reducer is ordered individually. The word count from each reducer is ordered by the key, right? But these two ranges, if you try to concatenate them, you will get a result like this. If you concatenate part 0 and part 1, you will not get the ordered data. Instead, you will get this kind of result. All right? And this that's where the complication of combining the results come into play. If you wanted that all the keys which are starting with a and b go to the first node while c and d should go to the second node, that you can do by defining combiner. There is a way, you can define combiner, and Hadoop will take that call. All right, now again, one quick overview to all of you again. All right, let me just go through the entire loop. Let me go through the entire loop. So when we wanted to store large files in HDFS, HDFS broke that file into blocks, and it also replicated the blocks on multiple nodes. Okay, so we have got multiple blocks having each one having multiple copies. All right, next is there is something called MapReduce. Now, MapReduce utilizes yarn to get the work done, but MapReduce expects us to write little pieces of code called map and reduces. Okay, while map dictates, our function has to dictate how the input record is going to be converted into key and the value, meaning criteria for sorting and the actual data. Based on this criteria of sorting, Hadoop is going to sort this data. Now, who is going to do the actual work? Hadoop MapReduce is going to do the sorting, but actual work is going to be delegated to Yarn so that Yarn can execute a particular piece of logic at various places. Okay, so actual work of execution of sorting, execution of your code, execution of uh, MapReduce code is going to be done by the way of Yarn. Yarn will be doing the main heavy lifting of executing processes. Okay, executing the processes on various nodes which do all of these things. All right, so split is going to be passed through the map function, producing key value pairs. And if you have multiple reducers, those results will be capped in those many buckets. If reducers are n, then there will be n buckets in which the output will be gathered on each machine's running map function. Okay, also please note that map function is being executed inside the same computer containing the data. That means there is no transfer happening, there's no transfer of the data is happening between the machine containing the data and till the point map is being executed. Okay, so that there's no transport involved. Now, but After the data has been sorted and split it into two buckets, these buckets are transported over the network to the machine running the reducer function. Okay, in case there is a single node which is having map, the chances are reducer will be run on the same node, because because it will reduce the total cost of transporting the data over the network. Okay, and once the data has been transported to the reduce, each reduce has gathered the data, then the merging will start. Then the merging of the data will start. All right. Oh, sorry, I have been using a wrong word here. The we call there is another word. It's not called combiner. It's not called combiner, the one which will split the data here. It's called what do you call that? Um, it's not called combiner. It's called I'll come back to that later. Okay, it's not called combiner, but combiner combines the data, not splits. All right, this data will be carried to these places. All right, and so each bucket will be carried here and merged. Since this bucket contains many keys, each bucket will contain hundreds of keys or thousands of keys or 10,000s of keys. These will be merged easily because they will be ordered. Okay, they'll be ordered, so it's very easy to merge the ordered data by using the same technique as merging. Okay, and same technique, because it's not too hefty, but executing reduce for each of the keys, because this result is going to be ordered. After merging, the result we expect will be ordered by the same criteria what is put down by the map function. On the same key, the result will be ordered, which means it is easy to group it. And after grouping, Hadoop will give you the list of values and the key. Now reduce will take key and the list of values and will be and and will produce a result combining all the values for key. Please note that if there are a million keys in your million distinct keys produced by map function, reduce will be executed 1 million times. Okay, and if each key was repeated 100 times, that means map function will be executed 100 million times. Okay, if there are 1 million distinct keys and each key was was having 100 different values, then then map function will be called 100 million times. Okay, and reduce function will be called a million times. Okay, keep that in mind. While the instance of map and reduce are 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 only few. Okay, instances of mapper are equal to the number of input splits, while instances of reducer are based on number of reducers we configure. All right, I have few things here. Mahesh's question is, in Hadoop 1.0, sort, copy, and merge were tasks of the developer prior to Yarn, or was it present in Hadoop? This was present in Hadoop 1.0 as well. Okay, so there has been no change in MapReduce. Okay, there has been no change in MapReduce when we moved from Hadoop 1.0 to Hadoop 2.0. It was only the architectural change, where the common part which could be used elsewhere was taken out from MapReduce and was named as Yarn. Okay, I think I should put it down properly, unnecessarily confusing you all. Okay, let me come again, Mahesh. If 1 million distinct keys and each having 100 values, okay, 100 values, then, okay, then total number of reducer function will be called 1 million times. Yes. All right. Does that make sense to all of you? All right. Now there's a question from Biswa. Where does combiner sit in diagram? Combiner sits here. After the map, combiner sits here. All right. Now there are few questions to all of you that you should think, and we should discuss it over the next weekend. Now question from Midley is each map and reduce function happening on different data nodes? Not really. Not really. Sometimes map and reduce might exist on each no, same node, sometimes on different node. But reduce functions will not be executed on different. Okay, I'll not try to confuse you. Let me try to draw a quick diagram. Okay, so imagine this. This is your big file. Okay, this is say two parts of the same file. Let me try to look at it this way. Okay, this is a single file. This one is on data node 1 and this is on data node 2. Okay, it's having a million lines. Okay, it's having a million lines. Okay, let me again correct it. I don't understand why. Okay, so imagine that this both of these imagine that both of these files contain many lines. Okay, these contains many text lines containing some text line. They contain many text line. Okay, here also it's containing many text lines. Okay, and so on. All right. For each of these, there'll be one mapper instantiated. Also, there'll be a thin layer, or you can say, we can say input split. Okay. So instead of this thing, let's assume that this has been data from data node has been loaded into input split. This one input is split, this one, and this is another input split, which is equivalent to the data block, but in a parsed and loaded. This is parsed and loaded and created the records. For each one mapper will be executed, created. Okay. Now, in each of this, in each of this, how can I move them like this? Okay. These are the mappers that have been created, and and these have been created for all of this. Okay. But there'll be map function called, okay, for each of the records in the input, for each of the records in the input, each of the records in the input, one particular map function will be called. For each line, for each of the input, the map function is being called on the same machine. So mapper will be instantiated per input split. Mapper 2 will be instantiated for the second input split. And mapper 1 contains a map function, mapper 2 contains a map function, and they will be executed many times. Okay? They'll be executed many times. Okay, or you can say the load function of mapper will be called only once. Okay, for each line, for each line we are each line our mapper function is being called. Okay, and they are producing key and value here. They're producing key and value. It's producing key and value. Make sense, or does it look really ugly? All right. Now, question from Mahesh is: each map function is sequentially called sequentially for each line or parallelly. All of this happens in parallel. Map function will also be called in parallel. Okay, does not will be called it will not be called in sequential. Did it make sense to you? I think Midli was asked that question. Midli, is that clear now? So these all of these map functions are happening on first node, and all of these map functions here will be happening on the second node. All right, I have some assignments before we go forward. Let me explain to you the assignments. Although that assignment is available in the LMS, you should definitely try try as much as possible. Okay, so first question is probably the easiest one. You have to compute the frequencies of letters. Will you use MapReduce or not? First question is, will you use MapReduce or not? Second question is, please use MapReduce to do the computation of frequencies of letters. Frequencies of letter, how many times A occurred in this, B occurred in this, C occurred in this, and so on. Okay, if a letter did not occur in in a text, we don't need that in the output. Okay, next is find anagrams in Hugh's text. You are given a Hugh's text, a billion words. There will be some words which are anagram of each other. For example, cat and tack and act are anagram of each other, meaning if you rearrange in some random order, if you rearrange the characters of a word in some random order, you will get different anagram. You'll get an anagram of a word if you rearrange it. Okay, any it doesn't have a meaningful anagram, doesn't have to be meaningful here. All we are saying is, in this given huge text there will be words which are anagrams of each other. So you have to find out what are those anagrams. Okay, you have to list down in the output that these are anagrams of each other, or you have to just bring together all the anagrams. Okay, so for example, the cat act in tic-tac-toe, the output we are expecting cat tack act in one line, then second line is the, and then third line is toe, and fourth line is in, and fifth line is tick. Okay, that's the expectation, and this output does not need to be exactly in the same order. So even if you are not good with coding, write the pseudocode. If you are not good with pseudocode, write the theory. Okay, but I mean, my personal choice would be somebody with either pseudocode or the code. Okay, because theory is very ambiguous. Third question to all of you is, there is a file that contains DNA, and this DNA is in this form. Okay, there's a file containing DNA sequences of people, and you have to find out people who have exactly same DNA. So first column, so the columns are separated by space. First column is user ID, second column is the DNA. You have to bring together the people with the same exact same DNA. Okay, so some researchers said that if people have same DNA, the chances are that they belong to the same father. Okay, so you have to bring the families together. All right, All right. Yes. Okay. Yes. It's asking that if I could go over this assignment again. So let's say given a huge text, you have to scan through the text, uh, okay, and find out which are the anagrams of each other. But you have to do it using MapReduce. Let's say there is an input file which contain the text, say the cat act in tic-tac-toe. The does not have any other uh, anagram in it, but cat has, because CAT, same letters are also existing in act and same letters are also existing in tick. Okay, but in different order. So all you have to do is bring all the anagrams together. Clear? Now DNA sequence problem is clear to everyone. Should I move to another problem? All right. Next problem is there is a file, contain same file, the one which we had earlier. Now another scientist came along. He came up with very interesting insight. He said that either the people who have identical DNAs or exactly reverse DNA. Okay, either two people should have exactly same DNA or exactly reverse DNA. They are all considered part of the family. For example, user 1, user 2 and user 4, their DNA is either identical. For example, user 1 and user 2, the DNA is exact reverse. ACGT, if you reverse it, it will become TGCA. That is the DNA of second user. And there is user number 4 who has exactly same DNA as user 1. So you have to bring families together as per this this particular insight. So this scientist, second scientist said that people if you bring people whose DNA is either identical or mirror image of each other, they will be of the same class, will be from the same family. So you have to bring families together in 3B problem. All right. I hope this is clear to everyone. Now the fourth problem is little tricky. It's little tricky problem. Although if you are coming from database, it's nothing but a simple join and group by. All right. In this strange democracy, there are the voting rights of people are not equal. Instead, it is proportional to their wealth. The person who is wealthy, his vote count will be considered more as compared to one who is poor. Okay, so you are given the bank account of all the people in this democracy, as well as the list of people who voted for who, and all you have to find out is who won the election. What is the final vote count of everyone? For example, A voted for A voted for C, B voted for C, C voted for F, A's worth is 5, B's worth is 1, C's worth is 11. Therefore, C, who has been voted by A plus B, the worth of C would be 5 plus 1, that is 6. F, who is voted by C, okay, and C's worth is 11, so F got 11. Okay, in an ideal democracy, C could have got 2 votes and F could have gotten 1 vote, but in this democracy, F won the election. So you have to give the overall vote count after doing this. Also, please note that there are few things which you have to keep in mind doing this. While feeding MapReduce, while telling that, hey, this is my input data to Hadoop, you can also tell that this is my input folder. All the files in that folder will be concatenated together and fed to your mapper. Okay, so you have to think about these problems and we will discuss the solutions to these problems in the next class. But be prepared, try to solve these problems by yourself. Okay, we will anyway discuss these to a depth, so you will be able to grab the answers very quickly if you have if you think over these problem, if you try to solve these problem using MapReduce. Okay, it'll be very easier for you to just reach to the conclusion quickly. Okay, it'll be very easier for you to learn this if you just think over it again after this class. All right, let's meet on next Saturday, and we start. For you, for some of you it'll be Friday. Okay, we'll see you then. Yes, pseudocode is good. All right, all right, everyone. So next weekend we don't have class. Lots of people have asked for it. Okay, next weekend we don't have class. We'll meet next to next weekend. All right, meaning next to next Friday. All right, next weekend we don't have class. All right. So most of people have already requested me that they'll to not keep the class. Okay, that's why I have kept it. All right, Abhay. Hope that's not a problem. All right. Yes, Biswa, but I can't afford to have the 2 weekends off. That'll be too big a problem for me. I had a problem. I mean, I had to take a call whether to keep it on the New Year Eve or on the Christmas. So I lots of people asked for the Christmas actually. Okay. All right, Biswa. Have a great holidays, and stay connected if you have a problem. Lakshmi, let me try to solve your problem, which we had discussed earlier. And okay, have a good time. Bye bye. Thank you, Mahesh. Mahesh is wishing Happy New Year to all. Yes, yes. All right. All right. So thank you, everyone, and have a great day. Okay. So I think this will be good. All right. So this is what everyone is saying. All right. Great. Have a good day. Bye bye. And yes, you can give me a call on my phone number, or you can basically write an email to me. Either thing is fine to me. All right. Bye bye. Have a good day.